Greetings comrades, my name is Gigantles, and as you can see from the title of this video, my video isn't going to be necessarily about various problems in my university life, but I'm going to be talking about what exactly my dissertation last year was about. And the reason why is because since I'm doing my masters now, I'm having to do another dissertation. And when I was busy trying to do preliminary reading for it, I thought to myself, hold on, I didn't tell you guys much about my dissertation from last year. So I thought I might as well just give a brief recap of what I studied. And I can't remember everything off the top of my head, but I'm sure that after the certain point in this video, you won't see my face anymore, lucky for you. And I'll just basically be narrating what I did, and then I'll give handy pictures and stuff to show you what I'm talking about. And also correcting any of the mistakes that I'm quite famous for making when it comes to videos like these. So, to understand what my dissertation last year was about, we need to go further back, and back to when I was in college. And for those of you in the US, our version of college, or sixth form, is the last 2 years of your high school. So, what I did in my college, I had 3 degrees that I was studying, and 3 A levels I was studying. And in the end of my first year, I learned that there was something called an EPQ, and that was that basically stood for an extended project qualification. And it technically it technically counted as a whole grade. So if you got a distinction in that, then that would help you. That would help improve your scores. For this EPQ, I decided, what if I focus on the effects of the KT extinction? Not the effects, the causes of it. Because until that point in time, I only thought that the Chicxulub impactor was responsible for that. But I'd been reading about the influence of the Deccan traps, which was basically a fissure eruption producing huge amounts of flood basalts. And for those of you that don't understand what a fissure eruption is, you know how basically a big volcano is just a big volcano, and then a supervolcano is an even bigger volcano. The fissure eruption is an even bigger volcano technically, and it's basically when you have a huge amount of lava coming out of a big crack in the ground, or big cracks, and it produces some of the largest igneous provinces on Earth. The Siberian traps, which erupted at the end of the Permian-Triassic boundary, technically caused the largest mass extinction in history, with something like 96% of all life dying, and that extinction event was known as the Great Dying. Meanwhile, the Cretaceous-Tertiary boundary, that extinction event was only like 87%. So yeah, there's a huge amount of lava produced during those fissure eruptions, huge amount of aerosols, all sorts of stuff, leading to big extinction events. The Deccan traps were somewhat similar. They had a huge role in messing up the climate of the Earth and inducing the volcanic winter and global warming and aerosols and poisoning and everything. There was a lot of stuff behind what the Deccan traps did, and I thought this would be quite interesting if I wrote about it. Now, when I was busy researching the Deccan traps, I ended up uncovering something called the Shiva structure. The Shiva structure is a proposed impact crater that would have had a lot of influence on the Deccan traps. And the history of this impact structure goes all the way back to the 60s, in which, I can't remember their names now, but one researcher looked at the Amarant Ridge by the Seychelles, and he believed it to be the rim of an ancient impact event. And then a few years later, him and another researcher believed that the Seychelles were actually the central uplift, or rather the top part of a huge igneous province that was the center of an absolutely massive crater. And this crater, they estimated, would be around 1,000 kilometers in diameter. And that is absolutely huge, because I believe the largest crater on Earth is the Verdefort Dome, sorry if I pronounced that wrong, and that's only like 300 kilometers across. So this would have been an absolutely huge crater, with the Seychelles as the central uplift, or I guess central plateau, whatever they call that. It would have been the center part of this massive crater. And the scientists drew inspiration from the lunar Mars, or lunar mares, craters on the moon that were flooded with lava, which is why which is why some parts of the moon look darker than others. However, over the years, this theory and model faced some scrutiny, and it was concluded that the reason why the northwestern half of this crater wasn't to be found was because the impact event had actually damaged the tectonic plate and caused a mid-ocean ridge to appear, which split the crater in half. So the southwestern half would be by the Seychelles, and the northeastern half would be by India. And a number of years later, a man called Dr. Chatterjee came along and believed that he had found the northeastern half. And this was pretty much off the coast of Mumbai, so in western India. He proposed a new crater model, which would have been by a tear-shaped model with the pointier end the pointier end by Mumbai, and the crater itself would have been 650 by 400 kilometers, so pretty substantial. But then the results of an ocean dredging mission by the Amaranth Ridge concluded that there were rocks present in the area that were far older than the Shiva structure forming during the KT boundary. So they said, okay, you know what, this can't be the same, this can't be an extension of that crater. So it faced a new revision, and the crater was reduced to a 500 diameter wide crater that looked somewhat it looked a lot squarer, similar to the Beringa crater in the US. I then had to do a lot of research about the structure of the crater and where Chatterjee proposed the central uplift was, where the crater rim was, and he believed that excluding the crater rim, there were 3 main rings surrounding the central uplift with huge annular troughs between them. And he said that it's unfortunate how a lot of the crater has been covered by marine sediments where the crater is underwater, and Deccan trap deposits where the crater is on land. So it's going to be quite difficult to do proper drilling there. However, he did look at some drill cores obtained by oil companies in hydrocarbon companies in the area, because if there's something hydrocarbon companies are good at, it's finding impact craters because of all the drilling they do. And he believed that when looking at their drill cores taken from marine drilling missions, that he had found underneath all of the post-impact sediments, there were impactite, so various rocks formed from the impact event, as well as crater melt and a brecciated crater floor. And in this brecciated crater floor, I believe it was, he claimed to find quartz grains or quartz crystals with pseudotacholites. And pseudotacholites are a type of glass that form during high pressure, high impact events. You can find them sometimes in volcanic deposits and underneath massive landslides, but they can also form in impact events. Shatter cones are the result of very high impact events that effectively shatter the rock beneath it in a strange horsetail pattern. And those are only found either under nuclear detonations, right underneath the center of the detonation, or in the central the central peak or the central uplift of an impact event. Unfortunately, though, it's quite difficult to find the central uplift in some places and get a drilling mission all the way down there. So there's a lot of work to be done to conclude that the Shiva structure itself is actually an impact event, or rather an impact crater. But Chatterjee and a couple of other guys who later on looked at the evidence, looked at the characteristics of the area where the Shiva structure was in, and they tried to extend what sort of influence that would have had on stuff like plate tectonics and impact deposits in the surrounding ocean and world. And one of the best pieces of evidence that they've gathered from what I've researched is from impact deposits. You see, there's a lot of different types of rocks and structures and mineralogies that are produced during an impact event. One of these is tektites. Tektites are remnants of host rock and stuff that was sent flying into the air during an impact event, where they melted, and as they fell to Earth, they crystallized into various forms of glasses. I've got a few tektites at home. They're they're shiny and black and they look a bit strange. But the importance of these tektites is that they preserve the host rock mineralogy and chemical signature. Okay, that's not mineralogy, sorry. They preserve the host rock's chemical signature, because it's effectively the host rock melted and then frozen again as glass. When you look at tektites from the KT boundary across Europe, Asia, the Indian Ocean, Oceania, and the Pacific Ocean, or the Western Pacific Ocean, you see that they all contain a chemical signature that is not compatible with that of the Chicxulub crater, because the Chicxulub impactor, it landed on a carbonate shelf, and this is one of the reasons why it was so deadly for the impact event. For the KT extinction event, because all those carbonates vaporized, flooded the atmosphere, was aerosols, lowered temperatures and everything. But this means that it would have had a very different chemical signature. Any tektites produced from the Shiva impact event would have been of basaltic origin, because the Shiva impactor basically landed slap bang on top of earlier Deccan trap flows. So all this basaltic rock would have vaporized, not really vaporized, they would have melted, flown into the atmosphere, and then they would have crystallized and started falling all over the world. And these tektites found all over the Eastern Hemisphere, have a much more similar chemical signature to the Deccan basalts than they do the carbonate shelf of the Chicxulub impactor. Chicxulub impact event. Another important thing to take into account is trajectory angle. The Chicxulub impactor is believed to have come in from a northeast direction, and at a very steep angle. I think it was like 60 degrees, so very steep. And the results of this would have meant that it's all over the deposits and stuff. All the stuff it would have thrown out would have formed deposits in a very narrow range, or in a very narrow. I can't think of the word now. A very narrow dispersal, and it would have only really covered maybe Central America, South America, and the Eastern Pacific Ocean. Whereas the Shiva impactor came in at a much more shallow angle. I think it was almost 30 degrees, and its angle of dispersal would have been something like 180 degrees. So on a map, this would have included all the way from Europe down to Oceania. Okay, an absolutely huge angle of dispersal. Huge. So what this means that if the Shiva impactor crash landed on the side of the Indian plate, then any fragments of that meteorite could have continued their trajectory all the way halfway across the planet before slamming down again. And this is quite interesting because we actually have a fragment of what is believed to be the Shiva impactor. It's of a very similar chemical signature to the Chicxulub impactor, but it's definitely not within the dispersal range. So either our estimates for the dispersal range of the Chicxulub impactor are off, or, and this is something else, and this leads to another interesting question, the Shiva impactor is responsible for this fragment. But if the Shiva impactor has a similar chemical signature to that of the Chicxulub impactor, then it's possible that both of those meteorites actually came from the same celestial body. One of Dr. Chatterjee's original claims about the Shiva impactor was that it and the Chicxulub impactor came from the same rubble asteroid. Because in space, there's various different forms of asteroids out there. There are three main asteroid types from what I remember. There's a normal celestial body, so just a single rock hurtling through space. There's a rubble asteroid, and then there's an asteroid family. An asteroid family is when you have an asteroid that has been broken apart through a huge impact event, and it's basically a collection of smaller rocks and dust that float around space. Then you have a rubble asteroid, which is an asteroid that has been fragmented in an earlier impact event, but due to its very weak gravity and ice, it's sort of holding itself together. So Dr. Chatterjee proposed that the Chicxulub impactor and the Shiva impactor were originally from the same rubble asteroid, and even drew a map of what he called was the impact belt, or as he named it, the Alvarez impact belt. And this rubble asteroid would have gone over. It would have passed over India, and then continued across the Pacific Ocean, over North America, and then over Europe. And this was important because there's also another impact that can be attributed to the KT extinction boundary. Maybe not necessarily the event, but at around the same time. And this is the Baltish crater found in central Ukraine. It's been made radiometrically dated to around 90,000 years around the Chicxulub impact event. So it's possible that if there wasn't a rubble asteroid floating in space at this point in time, it was orbiting the Earth and slowly fragmenting over several tens of thousands of years. But if not, then it would be quite interesting if both the Shiva impact event, the Chicxulub impact event, and the Baltish impact event were all caused by a fragmenting asteroid over the Earth. Of course, this would mean that there would be, other craters out there that we have yet to discover. This is a bit difficult to believe with so little evidence for it, unfortunately, due to lack of research. Not just because the odds of this would be absolutely and ironically astronomical, but also because it would mean that the Chicxulub impactor came from almost the exact opposite direction of what we believe it of the direction that we believe it came from. So right now it stands from a northwest direction, but northeast direction, but according to this, it would have come from the southwest. But it was definitely something to think about. Very interesting to consider the possibility of all of this rubble asteroid breaking apart and impacting across the Earth within a relatively short period of time and damaging the global climate and causing an impact and causing a huge extinction event. I also ended up doing research into the plate tectonic side of this, and I found that very interesting as well, because Dr. Chatterjee proposed that this impact event was so great it actually cracked the tectonic plate of India. Not only that, but it also sheared the deeper lithosphere of it. The Indian tectonic plate is quite an old tectonic plate, and when you look at other similarly aged tectonic plates, you see that all of them have quite a deep lithosphere. So this is the deeper rock that extends into the mantle that you find underneath continental plates, continental crust. But the Indian Ocean does not have this lithosphere. And in fact, if you look at the continental drift during the late Cretaceous, you see that the Indian tectonic plate was traveling almost 4 times faster than any other tectonic plate. And as I said, the impact event not only split the tectonic plate, but also sheared it, whilst providing a lot of momentum, or a lot of driving force behind the continental drift of this plate. So it accelerated the Indian tectonic plate as it crashed into Asia, and the sheer momentum of this impact event is one of the reasons why it continued pushing so hard into southern Eurasia, creating the largest mountain range on Earth, and also a massive uplift and plateau in the area. And before any of you wonder why this impact event didn't punch a hole through the tectonic plate of India, it's because it landed slap bang in the side of the Indian subcontinent, which would be a nice way to explain why the second phase of the Deccan Traps eruptions, which occurred at the KT boundary, which would be a nice way to explain why the second phase of the Deccan Traps eruptions produced almost 80% of its total material when you add in its first and third phase as well. The first phase contributing the basaltic material that the impactor would have impacted into and sent all those tektites flying around the world. And another interesting geological, or rather geothermal feature is what researchers described as the NAPSI structure. You see, fissure eruptions are not caused by normal processes of subduction that happen at plate boundaries. They're more similar to hotspot eruptions, such as Mauna Kea and Yellowstone, but they're on a much larger scale. And at the time of the KT boundary, the Deccan Traps were right over what is known as the La Reunion volcanic hotspot. So you had this huge amount of very hot rock that had basically split part of the Indian plate and was producing a lot of volcanic rock. And when the Shiva impact event happened and sheared the Indian deeper lithosphere, it reduced you could say almost like the buffer, the lithosphere buffer between the more shallow lithosphere and the mantle plume, which is why we end up having the Napsi structure. And although the Indian tectonic plate has drifted away from the La Reunion hotspot, there is still a 50-kilometer tall anomaly in the continental crust beneath the Indian tectonic plate underneath Mumbai and that surrounding region, which is where this thin lithosphere has allowed much warmer rock to make it closer to the surface, allowing that region of area to be more geothermally active. So hopefully all of you are still awake at this point in time, but the main thing I wanted to get out of my research from some of the evidence I've shared with you is that the Shiva structure it seems to be more than just coincidental, a lot of the stuff behind it, and I think that it's definitely worth investigating. Even if it is ruled out as an impact crater, maybe then we should find ways to explain how all these coincidences that look like an impact crater aren't. It would definitely help refine our methods of investigation when it comes to impact craters, but the point of it is I think it's definitely worth investigating. It would be quite expensive, but it would be an expense worth taking, or an expense worth making, to investigate not only just to investigate this structure, not just because of its implications for the KT extinction event, but also for its implications on the history of the Indian tectonic plate. I know I definitely waffled on for a bit, but hopefully you can hear how passionate I am, even if I'm not the best at narrating stuff. But yeah, I was glad with my dissertation. It helped me pass, and here I am doing a master's now. I'll tell you about what I'm doing in my next dissertation later on, but the main point of this video is that I do my research, and my research for my dissertation last year was about a potential impact crater in the Indian Ocean. Whether you think it is or not, that's up to you. Hopefully we do further research in the future, and we can provide a more definitive answer, which can either confirm it or later rest our I can't think of the right words now. I talk for half an hour and I can't think now. Either we confirm it's an impact crater, or we confirm it isn't, and then we can shelve that and then focus our efforts on trying to conclude why, despite this not being an impact crater, why it seemed like it was for so long, and how we can explain all this evidence that seemed to conclude it was an impact crater, even though it wasn't. Yeah, like I said, it could help refine our methods when it comes to investigating impact craters and other events relating to mass extinctions and the KT mass extinction. Otherwise, I'm just going to stop talking now, because I'm just going to bore you all. But again, that was my dissertation last year. Hopefully my dissertation this year, although it's more, I guess, narrow, it's in its field of study, hopefully it will contribute towards the field of volcanology. And maybe one day you'll be able to read more of my work online when I hopefully become a successful volcanologist. But that's it for this video, so thank you all for watching. God bless you all. See you in the next video, comrades. Until then.